Hello everyone and welcome. My name is Jason Gregerson. This is going to be a video key for Practice Exam 1. So we'll start with question number 1. Given the matrices shown below, state the values if they exist. Now, part A says what is the value in the 2, 3 position of A. So here we go, second row, third column. We'll have this value right here. So this will be 4. So remember that it is rows and columns. Then part B, similar type of question. Now we're going to the 2, 3 position of B. Second row, third column would be over here. Right, so this is an NA because there is no value in the 2, 3 position for this 3 by 2 matrix. Part C says what is the sum of A and B? Well, A is a 3 by 3 matrix and B is a 3 by 2 matrix, so this is also going to be NA. We can only add matrices if they have the same dimension. Next we have part D, which is 2B minus C. Now when we look at B and C, they're both 3 by 2 matrices, so we should be able to take this linear combination of these matrices here. So in this case, if I multiply the matrix B by 2, I am multiplying each of the components by 2, which will give me this result. And if I subtract off the matrix C, which is going to look like this matrix, the result, when I subtract these matrices, subtract them component-wise, so I will get a -1 here, and with -6 minus 2 is -8 here, -2, 2 plus 1 is 3, 2 minus 1 is 1, 0 minus 3 is -3. So this matrix represents 2b minus c. Next we have the inverse of D. So the inverse, to calculate the inverse, if our matrix was, if we had a general matrix that looked like A, B, C, D, our formula for the inverse is going to be 1 over AD minus BC times the matrix we get when we switch the values on the strong diagonal and change the signs on the off diagonal. So in our case, for D inverse, we're going to have 1 over 8 minus -3 times -2, which is +6, times the matrix when I switch the values on the strong diagonal and change the signs on the off diagonal. So in this case, it looks like I'm going to have 1/2 times that matrix, which will be 1, 3/2, 1, and 4 times 1/2 is 2. So this should be my matrix D inverse. Now on the exam, if I wanted to check that, I could verify that because if I calculated D times D inverse, I should be able to show that I would get an identity. So this would be a nice way to check your work if you had some extra time on the exam. All right, we'll go back up at the top, part F. What is the dimension of B? This is a 3 by 2 matrix. Remember, this goes rows and columns, rows by columns. What is the dimension of AB? Well, A is a 3 by 3 matrix, and B is a 3 by 2 matrix. These inside values match. That tells me I can do the multiplication. And the outside values will be the dimensions of the product. So whatever this value I get here of A times B, it's going to be a 3 by 2 matrix. So this will be a 3 by 2 matrix. What is AC? Now they actually want me to calculate this product. So I will write my matrix A, which will look like that, and my matrix C, which will look like this. In this case, once again, my product is going to be a 3 by 2 matrix, a 3 by 2 matrix. Now to calculate the first component, I'm basically going to take the first row of A times the first column of C. And so I will take the sum of the product of the components. So 1 times 1 is 1, plus 0 times 0, plus 2 times 1. That'll give me my first component here. And then I would just continue moving down the matrix. So now the next one will be the second row times the first column. I'm going to get -1 plus 4. And the last one will be 3 plus 2. This should generate my first column of this product here. Second column of the product is going to be the second column of C times the first row, then the second row, then the third row, so on and so forth. So here I'm going to have 2 plus 6, then -2 minus 1 plus 12, and 6 plus 6. When I simplify all these values, I'm going to get 3, 3, and 5, 8, 9, and 12. So this would be the product A times C. Next, I have A times D. Well, in this case, since A is a 3 by 3 matrix and D is a 2 by 2, my inside values don't match, this is going to be NA. I actually can't multiply those two matrices. Next, I have B transpose. The transpose of a matrix is what happens when I switch the rows and columns. So I'm going to take the first column of B and turn it into the first row, and the second column of B and turn it into the second row of B transpose. So that would be my matrix B transpose. All right, that wraps up page 1. Going on to page 2. Question 2 says label each of the augmented matrices below as in either row echelon form or row reduced echelon form. So here I can identify my leading non-zero values of each row. Those are my pivots. I do have zeros below those pivots in this case. However, the pivots are not equal to 1 and they're not zeros above this. So this is just going to be in REF form. And the next one, I have 2 pivot positions, the leading non-zero values of those rows. I have zeros below them, I have zeros above those, and I have 1s on the pivots. And lastly, I have a row of all zeros and I put it to the bottom. So this does satisfy all the criteria for being in row reduced echelon form. Question 3 says, for each of the row-reduced augmented matrices below, circle the pivot positions and then state which of the following best describes the solution set. It could be a single point, a line, a plane, or no solution. So I'll look at the first one. I've identified the pivots, the leading non-zero values of each row. The first thing I do is I check to see if there's a pivot in the augmented column. There is. That tells me that third equation would essentially be 0x1 plus 0x2 plus 0x3 equals 1. There is no value of x1, x2, x3 that would make that true. Therefore, in this case, there is no solution. If there is a pivot in the augmented column, there will be no solution. Next, I look at the next one, part B. There's my pivot, my one and only pivot. First, I check to see if there's a pivot in the far right column. There is not. That means there are solutions. I also see 2 free variables. Not only does that tell me infinitely many solutions, but because there's 2 free variables, my solution set would look like a plane in R3 in this case. The solutions look like a plane because there are 2 free variables. And then the last one, I circle my pivots. Once again, I check the last column. Is there a pivot in the far right column, the augmented column? There is not, so there are solutions. However, because there is a pivot in every other column, there are no free variables, so there will only be one solution. Our solution will look like a point in R3, just one solution. Question 4 gets into the true and false. True and false. Part A says a system with free variables is always consistent. And this is a false statement. And for a counterexample, we can actually look right up here to part A. Part A, in our previous question, had one free variable, x3 was free, however there were no solutions. Part B on the true and false says the augmented matrix has a solution if and only if B is in the span of the set A1 and A2. Well, if B is in the span is the set of all linear combinations, so that would be some number times the vector A1 plus some number times the vector A2. So if B was in the span, there would be a linear combination that would bring me to B. That just means that B is in the span if and only if there's a solution to this vector equation. And how do we solve vector equations? By forming the augmented matrix, doing a row reduction. So these are equivalent statements here. This guy is going to be true. Part C says elementary row operations can change the solution set of a system. That is false. Elementary row operations do not change the solution set. That's why we can do row operations to find the solutions. Part D, if a matrix has a pivot position in every row, then the associated linear transformation is onto. And that is a true statement. That is the definition, right? So basically, if there is a pivot in every row, then there's no way there could be a pivot in the augmented column. That would tell me there's always a solution. That would tell me for every b, there's at least one x. That's the definition of onto. So that will be true. Part E says, given an M by N matrix A, if M is less than N, then A must have linearly dependent columns. All right, so here it's easy to get the M and N's confused. So in this case, we have rows and columns. So I have M rows, N columns, and I have less rows than columns. So I'm just going to give myself a little example here. In this case, I have 2 rows, so I'll give myself 3 columns, maybe looking at some augmented matrix here. So the question is, if I have less rows than columns, are the columns linearly dependent? Well, if I have 2 rows, 3 columns, at most I could have 2 pivots, which means I would always have at least one column with no pivot. And that would tell me that the columns are linearly dependent. So this one is going to be true. So that's going to wrap up our true and false. The answers were false, true, true, and hopefully that explanation helped as we talked through those problems. We're into question 5. This is a fill in the blank session of the practice exam. So we'll look at the first one. It says the set of all linear combinations of a set of vectors is called the span of the set. B is if a matrix have a pivot position every blank, then the associated linear transformation is onto. And we can refer back to our true and false in this case. If there's a pivot in every row, the transformation is onto. If there's a pivot in every column, the transformation will be 1 to 1. Part C says a matrix equation in the form AX equal to 0 is called homogeneous. The homogeneous matrix equation is when that right-hand side is equal to 0. This equation is always consistent. Consistent just means that there are solutions. And so this system is consistent because we always know that x equals 0 is a solution. This specific solution, the x equals 0 solution, is called the trivial solution. The trivial solution. Question 6 says find the solution to the system of linear equations and express that solution in parametric vector form. So in this case, our first step is to write the augmented matrix for the system. So in this case, I will pull my coefficients 1, 2, 0, augmented with 3, -1, -2, 0, augmented with -3, and 2, 4, 1, and 2. There is my augmented matrix. Now part B says to do the row reduction. So I will rewrite my matrix here. And I will start to do my row reduction. My first operation is going to be row 2 plus row 1. Row 1 will stay the same. Row 2 will become 0, 0, 0, and 0. Row 3, my next row operation should be row 3 minus 2 times row 1. That's how I'll get a 0 in this position. I'll get a 0, 0, then I'll get a 1 minus 2 times 0, which is 1, and 2 minus 2 times 3, so 2 minus 6 is -4. From here, all I have to do is swap rows 1 and rows 3 to get this result, and this will be in RREF. So that is my row-reduced form of the matrix. Next, I have to write my solutions to the system in parametric vector form. So I write out the equation associated with each row, and this first row is going to be x1. I'm going to go ahead and subtract that 2x2 to the other side all in one step. So this will be x1 is equal to 3 minus 2x2. x2 is going to be my free variable because there is no pivot in the second column. And the second row gives me the equation x3 is equal to -4. Writing my solution in parametric vector form, I basically have 2 vectors. I have a vector of constants, 3, 0, -4, plus a vector of x2 stuff, which will be -2, 1, and 0. That should be my solution in parametric vector form. Moving on to question 7, it says determine whether or not the following sets of vectors are linearly independent or dependent. So in this case, I look at the first set of vectors, and I can always kind of try to eyeball it up at first, say, do I see that any of the vectors are linear combinations of the other, or maybe is 0 in the set? I can maybe look for some shortcuts to see if it's linearly independent, but if I don't see anything, I can always do the row reduction. And that's what I will do here. I will put these vectors into a matrix, I will do row reduction, and I will look to see if there's a pivot in every column. If there's a pivot in every column, that would tell me the columns are linearly independent. In this case, my row operation will be row 3 minus row 1. Row 1 stays the same, row 2 stays the same, row 3 becomes 0, 1 minus 2 is -1, 0 minus -2 is +2, looks like that guy. Next, I'm going to do a couple different operations here at once. That first row is going to stay the same. I'm going to take row 3 and subtract 2 times row 2. I can see those two rows are multiples. So when I do this operation, row 3 is going to be all zeros. And then I'll just clean up my row 2 by taking -1/2 times my row 2 to get 0, 1, -2 in that position. I see I have a pivot here, a pivot here. There is no pivot in the third column. That means these vectors are linearly dependent. Now I look at part B. Part B is a little bit easier because my set is only of 2 vectors, and I can always tell if 2 vectors are linearly independent or dependent by just checking to see if they're multiples. In this case, for me to go, there is no number I can multiply 0 by to get to 1. That tells me that these 2 vectors are not multiples of each other, which tells me that they are linearly independent because they're not multiples. Now notice I can do that for sets of 2 vectors, but I really can't do that for sets of 3 vectors because for 3 vectors I'm not checking to see if they're multiples, but rather I'm checking to see if they're linear combinations, and that's harder to visually determine. All right, question 8, find a linear combination of these vectors that yields the vector 3, -1, 1. So that means I'm looking to see, is there some number times this first vector plus some other number times this second vector that's somehow going to bring me to 3, -1, 1. So that statement of finding the linear combination that brings me to this vector is just saying solve the vector equation. To solve that vector equation, I just set up the augmented matrix and I do my row reduction. Here I'm augmenting with 3, -1, 1. All right, so I'm going to take row 2 plus 2 times row 1. My row 1 will stay the same. Row 2 becomes 0, and then 4 plus 6 is 10. And -1 plus 6 is 5. I'm going to do another row operation. I'm going to take row 3 minus row 1. 1 minus 1 is 0. -1 minus 3 is -4. And 1 minus -3, or 1 minus 3, is going to be -2. All right. I'm going to take 1/10 times row 2 to get 0, 1, 1/2. I'm going to take -1/4 times row 3 to get 0, 1 1/2. Now I'm going to take row 3 minus row 2. I'm going to get a row of all zeros. I'm going to let row 2 be the same. And then I'm also going to take row 1 minus 3 times row 2. That's going to give me a 1, 0. 3 minus 3 times 1 is 0. And then I'm going to have 3 minus 3 times 1/2. So 3 minus 3/2, which is going to be 3 minus 1 1/2, which will be 1 1/2 or 3/2. All right. So now I have completely row reduced my matrix. And so now I can see that my solution would be C1 in this case, X1 generally, but I'm using C1 and C2 for my variables, but C1 should be 3/2, and C2 would be 1/2. That tells me that if I were to take 3/2 times that first vector plus 1/2 times that second vector, that should lead me to 3, -1, 1. And I can kind of eye that guy up to see if it's correct or not. But this means that this is a linear combination of those other two. Number 9 says, is this vector in the span of these two vectors? And notice all these vectors are the same from question 8. And so we're demonstrating not a different question, but just a different way to ask basically the same question. The span of two vectors is the set of all linear equation or linear combinations, which means asking if 3, -1, 1 is in the span is just saying, is there a linear combination that brings us to us? It's exactly the same thing as the question from question 8. So the answer here is yes, because of that reason. So what we're demonstrating once again is that this is just another way to ask the same question. So we have to be strong on our vocab, so it doesn't matter how it's asked, we can still answer it. All right, moving on to question 10 about transformations, where here we have an equation for our transformation. We need to answer the questions. So our transformation, we can see here, is taking in a list of two values, right? So it's taking values from our 2 and mapping them to a list of three values. So our transformation is a mapping from our 2 to our 3. That tells us the domain is our 2 and the codomain is our 3. Next, we need to find a matrix that does the transformation. Two ways we could do that. We could transform the columns of the identity matrix, and the result will be the columns of A. That would certainly be one way we could do this. The other way is just to really say I'm inputting a list of two numbers. And I could just write that vertically like a vector to understand that input a little bit better. And if I just rewrote the output as a vertical vector, oh, I think I missed a comma in my original one here. I have a comma here, here, and here. That actually tells me this is mapping from R2 to R4. R4, which means our codomain is R4, not R3. There we go. And so once again, I'm writing out my vector. I have 2x2, I have x1 minus 3x2, and lastly I have x2. And when I write that output vertically, I can really see it's the matrix that looks like 1, 4, 0, 2, 1, -3, and 0, 1 times some vector x1 and x2, which means this is really the matrix that does the transformation. Part D says it's the transformation 1 to 1 onto both or neither. Now I can determine this if I can find the pivots for my matrix. So I'm going to take my matrix and I'm just going to do some row reduction until I can identify how many pivots I have and where they are. So in this case, my row operation is going to be row 3 minus row 1. Row 1 stays the same. Row 3 becomes 0. -3 minus 4 is going to be -7, 0, and 1. Now I'm not going to write down these row operations, but essentially I'm going to use this 1 to get zeros above it. So I'm going to take row 3 plus 7 times row 4. Row 2 minus 2 times row 4. Row 1 minus 4 times row 4. And the result is going to be 1, 0, 0, 0, 0, 0, 0, 1. From there I will just move the fourth row to the second row to get this as my row reduced matrix. Here I can see there's a pivot in every column, which means the transformation is 1 to 1, but there is not a pivot in every row, therefore the transformation is not onto. So I would say the transformation is 1 to 1, but not onto. And lastly, it says, what is the image of the vector 1, 2 under the transformation? That means what is the output if I were to input 1, 2? So I can just take my matrix and multiply it by my input 1, 2, and the product, which will be 1 plus 8, 0 plus 4, 1 minus 6 and 0 plus 2, this output that is 9, 4, negative 5, 2, that is the image of 1, 2 under the transformation. So that should be my image. Lastly, F. Is this vector 1, 0, 2, 0 in the range of the transformation? This is saying here's a possible output. Are we sure that there is an input that will bring me to it? So that's just saying if you have this matrix, is there some input that will lead to this output? And all that's really saying is solve the matrix equation. So to solve that matrix equation, all we're going to do is augment with our B, and we're going to do our row reduction. So as before, I'm going to take row 3 minus row 1. Here I have to be a little more careful because I do have an augmented column. I'm going to get 0, negative 7, 2 minus 1 is 1, 0, 1, 0 here. Once again, I'm going to use this 1 to get zeros above it. So I'm going to take row 3 plus 7 times row 4. Row 4 will stay the same. I'll have 0, 0, and negative 7 plus 7 times 1 is 0. 1 plus 7 times 0 is still going to be 1. Then I'm going to take row 2 minus 2 times row 4, 0, 0, 0. And row 1 minus 4 times row 4, which is going to be 1, 0, 1. Then I'm just going to reorder my rows. I'll have 1, 0, 1. Next I'll put row 4, which will look like this. Then I'll put row 3, which looks like this. And lastly, row 2. I'll identify my pivots. And in this case, I see there's going to be no solution because I have a pivot in the far right column, a pivot in the augmented column. No solutions means that that vector is not in the range. So this tells me that 1, 0, 2, 0 is not in the range of the transformation. All right, that wraps up our transformation page. Question 11 says solve the matrix equation AX equals B. So this just means we're going to create an augmented matrix and do row reduction. 1, 0, 3, 1, 1, 3 augmented with 1, 1. I'm going to take row 2 minus row 1. First row stays the same. Second row becomes 1 minus 1 is 0, 1 minus 0 is 1, 3 minus 3 is 0, and 1 minus 1 is 0. So only one row operation, we're already RREF. From here we're going to write out our equations. x1 is equal to 1 minus 3x3. Basically I took that 3x3 and subtracted the other side. And looks like x2 is equal to 0. There is no pivot in the x3 column, which tells me x3 is free variable. Lastly, I'm going to write my solution in parametric vector form. In each of these expressions, these equations, I see constants and then x3 components. So that means I'll have a vector of constants plus a vector of x3 stuff, negative 3, 0, 1, in my solution in parametric vector form. So there is my solution in parametric vector form. Question 12 has us complete the properties involving the matrices A, B, and C. So the first one is the transpose of a sum, which happens to be the sum of the transposes. That is a property I can use. Part B is the inverse of the inverse. The inverse of the inverse is just the original matrix. Same is true for part C. The transpose of the transpose is also just the matrix. D says the inverse of the product, which is the product of the inverses, but they have to be in the opposite order. Part E is the transpose of the product, and once again, transpose of the product is the product of the transposes, but in reverse order. And then part F, we're using the distributive property to write this as AC plus BC. Now notice this C is multiplying the quantity A plus B from the right, and therefore when we distribute it, C needs to stay on the right. Please note this is not equal to CA plus CB. That is not true. So make sure you're careful about what side that multiplication is done on. Question 13. Question 13 says calculate the inverse of this matrix and use it to solve the equation AX equals B. Step 1 is to calculate the inverse. Because it's a 3 by 3 matrix, we can't get away with that little formula that we used in the first question. Instead, we need to augment with the 3 by 3 identity matrix. It's going to look like that. And we need to do our row reduction. So in this case, I'm going to take row 2 minus row 1, which will give me 1 minus 1 is 0, 1 minus 0 is 1, 3 minus 3 is 0. 0 minus 1 is negative 1, 1 minus 0 is 1, and a 0. I'm also going to take row 3 minus 2 times row 1. I'll get a 0 here, a 0. 7 minus 2 times 3 is 1. 0 minus 2 times 1 is negative 2. I'll get a 0 and a 1. One more row operation step, it looks like. I need to get a 0 in this position right here. So I'm going to take R1 minus 3 times row 3. Row 3 will stay the same. Row 2 will stay the same. Row 1 becomes 1, 0, 0. 3 minus 3 times 1. 1 minus 3 times negative 2 is going to be 7. I'll get a 0 and a negative 3 here. So it looks like my inverse matrix, A inverse, is going to be 7, 0, negative 3, negative 1, 1, 0, negative 2, 0, 1. So I started with A augmenting with the identity matrix. We do row reduction until we get identity on the left, and whatever is gathered up on the right, that's the inverse. So there's my inverse matrix. Now how do I use it to solve the matrix equation? Well, in general, if I have the equation that looks like AX equals B, I multiply both sides by the inverse. Inverse times A is identity, and identity times X is just X. So the existence of the inverse tells me that this is actually my solution. So if I want to solve the equation, all I have to do is take my inverse and multiply it by the vector B. In this case, I'm going to get 7 plus 0 minus 6, negative 1 plus 0, negative 2 plus 0 plus 2. Looks like I should get the value 1, negative 2, and 0. And that should be my solution. 1, negative 2, 0. All right, question 4 gets us in the application problems. For this first one, the first step is to represent each molecule as a vector and write the associated equation. So in this case, I would have some number of the first molecule, and this first molecule looks like 3 atoms of sodium, 1 phosphorus, 4 oxygen, 0 barium, and 0 nitrium. I'm going to add the second molecule, which will be 0 sodium, 0 phosphorus. It's going to be 6 oxygen because I have 3 of this little piece times 2. So 6 oxygen, 1 barium, and 2 nitrogen. Now, really this would be plus X3 times the next molecule and plus X4 times the next molecule. But that will be my equation, and all I'm going to do is actually subtract those values over ahead of time. So this will be plus X3 times a vector that has negative values here. So this will be 0 sodium, 2 phosphorus, so I'm going to write negative 2 there. It's going to have negative 8 oxygen and 3 barium and 0 nitrogen. All right, plus X4 times negative 1 sodium, 0 phosphorus, -3 oxygen, 0 barium, and -1 for nitrogen. And this should equal the 0 vector. So that is the vector equation I need to solve in order to balance this chemical equation. So what I'm going to do is write my augmented matrix: 3, 0, 0, -1, 0, 1, 0, -2, 0, 0, 4, 6, -8, -3, and 0, 0, 1, -3, 0, 0, 0, 2, 0, -1, and 0. All right, so there's my augmented column. There's my matrix. Now I got to find a way to do this row reduction. This row reduction might be a little bit tedious. Lots of different ways you can go through this. I always try to avoid fractions, so I'm actually just going to swap out row 1 and row 2. Now that I've swapped those two out, I can get zeros below my first pivot by taking row 2 minus 3 times row 1. Row 1 will stay the same. Row 2 becomes 0, 0, 0 minus 3 times -2 is positive 6, -1 and 0. Then I'm going to take row 3 minus 4 times row 1 to get a 0 in this position. 6, 0, -3, and 0. And then I'll write the next two equations down here. Next two rows. From here, I'm going to do another row swap. I'm going to swap rows 2 and 4. Once again, the goal here is kind of to avoid fractions. So I'll have 0, 1, -3, 0, 0. I'll have 0, 6, 0, -3, 0. And then I will have 0, 0, 6, -1, 0. And lastly, 0, 2, 0, -1, 0. Now I'm in position to use that second pivot to get zeros below it. To do that, I'm going to take row 3 minus 6 times row 2. All right, row 1 stays the same. Row 2 stays the same. Row 3 becomes 0, 0, 18, and -3. Row 4 will stay the same. And my new row 5 will be row 5 minus 2 times row 2. I'll get 0, 0. I'll get 0 minus 2 times -3 is positive 6. And I will get -1. Now what I can see here is that rows 3, 4, and 5 are actually all multiples of each other. So because of that, I know I will be able to use row 3 to eliminate rows 4 and 5. So I will do that, and that will generate zeros for rows 4 and rows 5. And that will also take row 3 and divide it by 18, multiply it by 1 over 18. I'll get 0, 0, 1, and then I will get -1/6 there, -1/6. All right, from there, now I just need to get these two positions zeros, zeros above that pivot. To do that, I will take row 2 plus 3 times row 3. Once again, these last rows will be all zeros. They will stay the same. Row 3 will stay the same. Row 2 will now become 0, 1, 0. And I'm taking 0 plus 3 times -1/16. So that's going to be -3 over 6. I think I said 16th there, I mean 6th. So I will take -3 over 6, which is -1/2, and 0. My next row operation is going to be row 1 plus 2 times row 3. I'll get a 1, 0, 0, and 0 plus 2 times -1/6, which will be -1/3. That is my solution in parametric vector form. We'll write out the associated equations. x1 is equal to 1/3 x4. x2 is equal to 1/2 x4. x3 is equal to 1/6 times x4. And x4 is my free variable. All right, so now we have our parametric form of the solution. And the last thing we do is balance the equation. So to balance the equation, we're going to basically choose one solution where we choose the best value for x4, the smallest value of x4, that's going to lead to all integer solutions. So I'm going to let x4 equal 6 in this case. That means that x3 will be equal to 1, x2 will be equal to 3, and x1 will be equal to 2. For my original equation, my original problem, that tells me that I need 2 of my first molecule plus 3 times my second molecule, and that should balance out my equation, giving me 1 of my third molecule plus 6 of my last molecule. And that would be my balanced chemical equation. All right, one more problem to go. It's our network problem. And in this problem, we have some sort of network, and we are trying to solve our system to find the relationship between the different flows in our traffic pattern in this case. So to do that, we're going to look at each individual node. I have node A. When I look at node A, I have inflows and outflows, and my task is to set them equal to each other. So at node A, I have just x1 flowing in, and the inflow of x1 must be equal to the total outflow. The outflow is x3, x4, and 40. That means x1 is equal to x3 plus x4 equal to 40. When I look at node B, I will have just one value coming in, that is 200, and flowing out will be x1 plus x2. At node C, I'll have two values flowing in, x2 flowing in and x3 flowing in, and flowing out will be x5 plus 100. One more node to go, it's node D. And for node D, it looks like I have x4 plus x5 flowing in and only 60 flowing out. So these are the four equations that represent my system. Now to actually solve these, I want to put them into more of a familiar form. So I will put my variables on the left and my constants on the right. First equation is x1 minus x3 minus x4 equals 40. The next one's going to be x1 plus x2 equals 200. Then I have x2 plus x3 minus x5 is equal to 100. And lastly, x4 plus x5 is equal to 60. All right, from here, I'm going to go ahead and write out my augmented matrix. My augmented matrix is going to look like 1, 0, -1, -1, 0, augmented with 40. Then I'm going to have 1, 1, 0, 0, 0, augmented with 200, and 0, 1, 1, 0, -1, 100, and lastly 0, 0, 0, 1, 1, and 60. Now I have my augmented matrix and I can do my row reduction. My first row operation is going to be row 2 minus row 1. My row 1 will stay the same. My new row 2 will be 0, 1, 1, 1, 0, and 200 minus 40 is 160. From there, I will write out my second and third rows. Now I need to get a 0 in this position. So now I'm going to take row 3 minus row 2. First row stays the same. Second row stays the same. Third row becomes 0, 0, 0. 0 minus 1 is -1, -1. 100 minus 160 is negative 60. 0, 0, 0, 1, 160. All right, from here, I can see that row 3 and row 4 are the same. So from here, I'll take row 4 plus row 3. That's going to give me a final row of all zeros. I'm going to multiply row 3 by a negative 1. This will give me 1, 1, and 60 here. And then I'll write out my other rows. All right, so now I have a pivot position here, here, and here. I just have to get pivots above, or zeros above those pivots. So my next row operation is going to be row 2 minus row 3. All right, last row of all zeros. Then I have row 3, which will stay the same. Then row 2 minus row 3 is going to give me 0, 1, 1, 0, negative 1, 160 minus 60 is 100. And then I'm also going to take row 1 plus row 3 to give me 1, 0, negative 1, and then 0, 1, and 0 plus 60. Although I think I made a slight mistake here. I believe this guy should be 40, which means this guy should be 40, which means this guy should now be 100. So it looks like I lost a 40 along the way, but there I think I've caught that issue. So now I believe I have my final augmented matrix in row-reduced echelon form. From here I can start writing out my solution. That first row tells me x1 is going to be equal to 100 plus x3 minus x5. x2 is going to equal 100 minus x3 plus x5. x3 is going to be a free variable. x4 is going to equal 60 minus x5, and x5 is going to be a free variable. So there will be my solution in parametric form. Part B says when x4 is equal to 0, what is the minimum value of x1? So when x4 equals 0, since x4 is equal to 60 minus x5, if x4 is equal to 0, that would tell me that x5 must equal 60. Now because x1 is equal to 100 plus x3 minus x5, so minus 60, that tells me x1 is equal to 40 plus x3. And we're looking for the minimum value of x1. Well, x3 has to at least be positive because we're talking about traffic flows, so we can't have a negative flow here. So if x3 is its smallest possible value, which is 0, then x1 would have a minimum value, has a minimum value of 40. So that would be the minimum value of x1 based on those other criteria. All right, and that wraps up this practice exam key. Remember, the goal is to talk through the key so that you can work through your problems, you can verify your answers against the key, and if you have questions about the key, you can look back here and listen to the explanation. That wraps up this solution. Thank you very much.